Welcome back, everybody, for another deep dive. This time we're going to be talking about something that's really exciting to me. How computers and AI are changing mathematics.
Oh, yeah.
And I'm not talking about like using computers to do calculations.
Right.
We've been doing that forever. But this is different.
Yeah, this is way more interesting.
This is about proving theorems, discovering new connections, maybe even formalizing really complicated mathematical arguments.
It's incredible.
So like a whole new era
It is.
to the field. And to help me go through this, I've got an expert here.
I don't know about expert, but I'm happy to be here.
Well, you know more about this than I do.
And it really is fascinating because it's not completely new. The use of computers in math has a long history.
Yeah.
But what we're seeing now is, as you said, it's a step change.
Cool.
It's a fundamental shift in how math is done.
Right. We've had calculators and computers crunching numbers for ages.
Right. But we're talking about something deeper.
Way deeper.
We're talking about computers helping us understand the structure of mathematics.
The structure of mathematics itself.
Exactly.
Yeah.
So let's...
It's like those old logarithm tables from centuries ago.
Oh, wow.
Yeah. Those were crucial before modern computers.
I never really thought about that.
Like even the prime number tables that Gauss and Legendre used to formulate the prime number theorem.
Oh, yeah.
Those tables were all compiled by human computers.
Oh, that's right.
Incredible, isn't it?
It really is.
The desire to compute and to find patterns has driven math forward from the very beginning, and it continues today.
Totally. Yeah. And like even the online encyclopedia of integer sequences is still going strong.
Oh, absolutely. It's like a modern-day tool for discovery.
Yeah, it's a treasure trove for mathematicians.
It is. It allows you to search for patterns, to connect different areas of math,
Totally.
even to stumble upon new conjectures.
Yeah, and there's so much data in there, right?
It's massive, almost like a Google search engine for math.
So we've talked a little about the history. A little bit.
But what about the most dramatic changes that are happening now? Where are we seeing those?
There are three key areas, I think, that are driving this transformation. Formal proof assistance, machine learning, and large language models.
Oh, wow.
Each one has the potential to revolutionize things, but the real excitement is when you combine them.
Oh, so they're like more than the sum of their parts when you put them together.
Definitely. But before we dive into that, let's start with the formal proof assistants.
Okay.
They sound intimidating,
I'll admit, a little bit.
but think of them as really meticulous proofreaders for math.
Okay.
So a formal proof assistant is a software system where you break down each step of your proof into a sequence that a computer can verify.
Oh, man.
It's like writing a program, but the program is the proof.
So mathematicians usually use a lot of shorthand,
All the time.
and a computer needs it all spelled out. Right?
Yes, exactly. Mathematicians have this implicit understanding with each other.
Yeah, we get each other.
But a proof assistant, there's no room for ambiguity.
That makes sense.
Everything has to be defined precisely.
It sounds tedious.
It can be, but the payoff is certainty.
Certainty.
With a formal proof assistant, you can be absolutely sure that your proof is correct.
Oh, wow. So that's really the payoff.
There's no chance of a subtle error slipping through, which is crucial for complex proofs.
Because those are easy to mess up, even for the best.
Oh, yeah. Even the best mathematicians can make mistakes.
So it's like having this program double-check your work with incredible precision.
Exactly.
But are there any real-world examples where this has been important?
Oh, absolutely. Take the four-color theorem, for example.
But the map one, right?
That's the one. Any map can be colored with just four colors, so no two adjacent regions are the same color.
I remember that one.
The original proof involved checking so many cases they needed a computer program.
Oh, wow.
But even then, there were doubts about the program itself, so it took years to formalize the proof using a proof assistant called cuck.
So now we're completely sure.
Exactly, a level of certainty that wouldn't have been possible otherwise.
That's wild.
It is, and there's another example, the Kepler conjecture about packing spheres.
Oh, yeah, that was a tough one.
It also had a computer-assisted proof, but the formal verification took over a decade.
A decade.
With a project called FlySpec, these examples show the incredible effort involved, but also the payoff in terms of confidence and certainty.
Yeah, so it seems like it's taking some of the most complex results in math and turning them into something a computer can understand and verify with absolute certainty.
Yeah, it's like a translation process.
The translation process.
It can be painstaking. Formalizing a proof can take years, often involving large collaborations.
Wow, okay, so what's the value of this?
Well, first, rock-solid confidence in complex proofs.
Okay, that makes sense.
Second, it can actually help us find errors in the original human-written proof.
Oh, wow.
And third, And perhaps most important, it allows us to build shared libraries of verified mathematical knowledge.
So we're building this foundation of mathematical knowledge that's completely checked and double-checked.
Precisely.
Oh, wow.
And this also has huge implications for how we teach and learn mathematics.
Really? How so?
Imagine textbooks and papers that have formally verified proofs.
Okay.
Students interacting with these proof assistants.
Yeah.
Mathematicians collaborating on these formalizations.
Wow.
It could completely change how we think about math, knowledge, and education.
That would be amazing.
It would be a whole new world.
Well, this is already blowing my mind.
It's pretty incredible.
And we've only just started.
It's just the beginning.
So that was formal proof assistant.
It's pretty intense, right?
Yeah, a lot to wrap your head around.
Yeah.
But let's shift gears a little bit
Right.
and talk about machine learning.
Yeah.
I mean, everybody's talking about AI these days.
It's everywhere.
So how's it impacting pure mathematics?
It's a really powerful tool for finding patterns.
Yeah.
But there's a difference in how it's used in math versus, say, like image recognition.
Okay, what's the difference?
So in a lot of applications, machine learning is used for prediction. And even if we don't understand why it makes a prediction,
Right.
as long as it's accurate, it's
Yeah.
useful. Think of like spam filters.
Right, they just work.
They do, but in math,
Math is different.
it's not just about getting the right answer. It's about understanding the logic behind it.
The why.
Exactly. Mathematicians need rigor and certainty.
Absolutely.
We need to know not just that something is true, but why.
Yeah, that's kind of the whole point.
Exactly. And that's where things get a bit trickier with machine learning.
Okay, so are you saying that machine learning isn't really suitable for pure math?
No, not at all. It's more that we need to be careful about how we apply it.
Okay.
It's not about replacing mathematicians.
Right.
It's about having a new tool.
Okay, got it. So how are mathematicians actually using machine learning in a way that works?
One example is in the study of complex systems like fluid dynamics.
Oh, wow.
There are equations that describe how fluids move, but they are so hard to solve directly.
They're really complicated, right?
They are. So researchers have started using what are called physics-informed neural networks.
PNNs.
PNNs, yeah.
So these PNNs are helping mathematicians understand these really complicated problems.
Yeah, they're finding approximate solutions that we couldn't get before.
So they're helping to get a handle on things that were previously just way too complex.
Exactly. And what's really cool is that these PNNs can reveal patterns
Okay.
that mathematicians might not have seen on their own.
Like they're showing us things we wouldn't have been able to predict.
Exactly. For example, how fluids transition from smooth flow to turbulence.
That's a classic problem.
It's baffled scientists forever.
And AI is helping to figure it out.
It might. It's giving us new insights.
So even though the PNN doesn't give us a rigorous proof,
Right.
it's offering valuable insights that could lead to new discovery.
Exactly. It's a new tool for exploration.
I like that.
And there's another fascinating example from knot theory.
Knot theory, like the mathematical knots.
Yes, exactly.
How does machine learning fit in there?
Well, researchers used it to uncover a relationship between different types of knot invariants.
Oh,
They trained a model to predict one type of invariant based on another.
interesting.
And then they used something called saliency analysis to figure out which features of the knots were most important for the predictions.
Saliency analysis, what's that?
It's basically a way to figure out which parts of the data the model is paying the most attention to.
Okay.
And get this, it led them to a brand new mathematical conjecture,
Wow.
which they were then able to prove rigorously using traditional methods.
So the machine learning wasn't just crunching numbers, it was helping them come up with a new idea.
That's exactly right. It really shows how machine learning can be a catalyst for new math.
Even if it can't give us that final proof.
Right. It's a partnership.
The best of both worlds.
Exactly.
Okay, so we've covered formal proof assistance and machine learning, but we have one more big one. Large language models.
The LLMs. Yeah.
These are things like ChatGPT. What's their role in all of this?
They're interesting because they work with natural language.
The kind of language we use every day.
Exactly. They can generate text, translate languages, even answer your questions.
I've played around with them.
Yeah, they're pretty amazing.
It's kind of freaky how good they are.
It is.
But can they actually do math?
That is the question.
Yeah.
And the answer is complicated.
Okay.
They can do some things like simple calculations, basic algebra,
Yeah.
but more complex math reasoning is tough for them.
Okay, what is that?
One challenge is that they can sometimes just make stuff up.
Really?
Yeah, they can generate text that sounds plausible, but is completely wrong.
Like they're hallucinating.
Exactly, and in math, that's a big problem.
Right, because you can't just say 2 plus 2 is 5.
Exactly, they don't always grasp the underlying concepts.
So it's like they're mimicking human language without actually understanding it.
Yeah, they can write about a theorem without truly understanding it.
So are they just a novelty then when it comes to math?
Not necessarily, even though they might not be writing complex proofs anytime soon.
Yeah.
They can still be incredibly helpful.
Okay, how so?
For example, I've found them very helpful for generating code,
Oh, interesting.
cleaning up data, suggesting research papers. It's like having a really efficient assistant
That makes sense.
to handle the tedious stuff.
Yeah, and I know programmers are already using them to help write code.
Oh yeah, like GitHub Copilot.
Yeah, exactly. Have you had any experiences where an LLM has surprised you in a math context?
You know, there was this one time I was working on a problem and using an LLM to help write code.
Okay.
And I was about to estimate a mathematical integral using this specific technique, and the LLM predicted what I was going to do.
Really?
Yeah, it suggested the exact code snippet for the method I was about to use.
It was reading your mind.
It felt like it, a glimpse into their potential to really understand and augment human reasoning.
Wow, that's incredible.
It is, but we're still in the early stages here.
Yeah, it's all so new.
It is.
Okay, so we've got these 3 incredibly powerful technologies.
Formal proof assistance, machine learning, LLMs.
Yeah, it feels like we're just scratching the surface.
Oh, absolutely.
But what about the big picture? How are they coming together to really transform math?
That's where it gets really exciting, because by combining them, we can envision a future where AI is not just a tool, but a collaborator.
Wow, a collaborator.
We'll delve into that and more right after this quick break.
Welcome back to the Deep Dive. We've been talking about machine-assisted proof.
Yeah, how computers and AI are becoming more and more important in mathematics.
We've seen how formal proof assistants are adding rigor,
Right, a level of certainty we've never had before.
and machine learning is helping us find patterns in these complex systems.
Things that would have taken us forever to figure out on our own.
And then there are the LLMs, those large language models.
Yeah, with their amazing ability to understand natural language.
It's like they're breaking down the barriers between humans and computers.
In a way, yeah, making these powerful tools more accessible.
It's mind-blowing to think about how all of these technologies are coming together.
It really is. It feels like we're on the verge of something big.
Like a whole new era of mathematical discovery.
Exactly, one where human ingenuity is being amplified by the power of AI.
Imagine a future where mathematicians can just talk to these tools.
Yeah, just ask a question in plain English.
Like, what's the best way to solve this equation?
Or, can you show me a proof of this theorem that I can actually understand?
That would be incredible.
It would democratize these tools, make them available to everyone.
Not just the computer science experts.
Exactly. It would be like having a conversation with a brilliant colleague.
One who has access to all of this incredible knowledge and computing power.
And who can see connections that we might miss.
It's like we're creating a global hive mind for mathematics.
Yeah, where everyone can contribute and benefit from the collective intelligence.
And as these tools become more powerful,
We can start to think even